So the title has been announced. So let me see. Okay, the abstract of my talk is I'm going to speak about quasi-linear elliptic equations of the following type. On the left, I have minus the p-Laplacian operator. I will give you a definition very shortly. And the right-hand side involves some force terms. So it equals, so minus delta pu equals sigma, which is a non-negative coefficient, times the solution u to the power q plus the datum mu. Let me consider this equation on the entire n space Rn. And I will mostly focus on the subnatural growth case where q is positive but less than p minus 1. But also, if I have enough time, I will touch the case where q is greater than or equal to p minus 1. Okay, so the coefficients sigma and mu are generally non-negative measurable functions or even locally finite measures on the Euclidean space Rn. And I'm going to present some sharp point-wise estimates of solutions to such equations, and also discuss criteria for existence and uniqueness of solutions. And my point is that I will be talking about general solutions. So in order to make the right-hand side well-defined, let us assume that u is in LQ locally with respect to the measure sigma. And then solutions could be unbounded. I will be more precise in a second. But in particular, we will talk about, for instance, Bmo solutions or solutions of finite energy, as well as general solutions, general weak or generalized solutions. Most of the results carry over to the general a Laplace operator in place of the p-Laplace operator. Of this form, the divergence of some function a of x and delta or nabla, okay, and I will specify the restriction on this function script a later on. Also, it covers fractional Laplace operators on Rn. Alpha could be anything between 0 and n. So my talk, today's talk, is based in part on joint work with my former students, Nguyen Con Phuc, Da Tien Cao, and Edisak Sisanya. Okay. Let me mention a few publications, recent ones related to my talk, and I will be making references to some of these results. Most closely related to today's talk is publications 1 and 2, very recent, and also 3 and 7, where I introduced jointly with Da Tien Cao a new type of nonlinear potentials which are closely related to such equations. Okay, so more precisely, we will discuss generalized solutions to this equation here, equation 1. So u is non-negative and solutions are assumed to be non-trivial. So not 0 everywhere and not infinity, at least at a point. The p-Laplacian is this quasi-linear operator, okay, the divergence of the gradient of u, absolute value to the power p minus 2 times the gradient of u. P is greater than 1 here, and the exponent q is positive. So mu and sigma are generally simply locally finite Radon measures. And as I mentioned before, more general a Laplace operators of the p-Laplace type could be covered as well. The case where q is equal to p minus 1 is called the natural growth case. It corresponds to Schrödinger's equation if p is equal to 2, and we simply have the Laplacian on the left-hand side. And then when p equals 2, we have this equation, semi-linear equation, but it is sublinear because we concentrate mainly on the case where q is between 0 and 1. So such equations have been studied extensively, starting from this work by Mark Krasnoselsky back in the 1960s, and also Brzezis and Oswald. These two references study equations of this type in nice bounded domains with nice coefficients, okay? But then in this 1992 paper, a very influential paper by Brzezis and Kamin, they studied such sublinear equations with mu equal to 0. And they studied bounded solutions, non-trivial bounded solutions when mu is 0 on the entire space. Now, most of the results that I'm going to talk about today are new, even for sublinear equations on Rn. Okay, so we're going to work with pretty general coefficients. And so I wish to introduce some concepts related to classes of measures on the entire space here. So the p capacity, a standard capacity, which is associated with the p Laplacian in a natural way for a compact set K, is defined as follows. It is a solution to this variational problem. We take the infimum of the Dirichlet norm of u raised to the power p, and the infimum is taken over all functions, say nice smooth functions with compact support, which are greater than or equal to 1 on this compact sets. Capacities, sets of capacity 0 plays an important role in studies of Sobolev spaces, so it's a natural analog of sets of Lebesgue measure 0 for Lebesgue spaces. In any case, if we go back to our equation 1 with p greater than 1 and q positive, it could be shown that if sigma is the coefficient at u to the q, let me show you again. So if sigma is this coefficient here in equation 1, then this measure sigma is necessarily absolutely continuous with respect to the p capacity, which means that if the capacity, for instance, of a compact set is 0, then the sigma measure of this set must be 0. More precisely, whenever we have a solution, a non-trivial solution to our problem, for instance, if q is less than or equal to p minus 1, then we have this estimate, which was proved in my paper with Carl Dutt. It says that the sigma measure of a compact set is bounded by the p capacity raised to the power q over p minus 1 times this LQ norm of u over k with respect to d sigma raised to the corresponding power. And recall that u is locally in LQ, so this second factor is finite. And so if the capacity is 0, then obviously sigma is 0. Okay, so this is a necessary condition, and it actually simplifies our study of such equations significantly. Okay, next, let me introduce some nonlinear potentials related to quasi-linear problems. Okay, so I'm not sure if you are familiar with these concepts. So let me, and please feel free to ask questions if you have any. So the so-called Wolf potential, or more precisely, the Havin-Mazia-Wolf potential, for a measure mu, locally finite measure, is defined as this integral from 0 to infinity. Here in the numerator, I have the mu measure of a ball, center that's x of radius r, divided by the radius of the ball to the power n minus alpha p, all of this is raised to the power 1 over p minus 1 and integrated against dr over r. So this is a nonlinear potential. So such potentials were studied by Havin and Mazia originally, and then by Hedberg and Wolf in applications to the spectral synthesis problem for Sobolev spaces. I will say a little more about that later on. But we will be interested in applications to quasi-linear problems. We will be interested in the special case where alpha equals 1 here. And let us denote such Wolf potentials simply by W sub P, okay? And it is easy to see that such potential is not identically infinite, or equivalently, it is finite quasi-everywhere with respect to capacity, which means it is finite everywhere except for possibly a set of p capacity 0, if and only if you have this condition here. Okay, so the integral is from 1 to infinity. We can assume that this ball is centered at the origin. Okay, so, and we will be assuming that this is true, otherwise our problems have no solutions. Now, let us recall linear potentials, or those are the classical Riesz potentials introduced by Marcel Riesz, so of order, say, 2 alpha. So here is the definition. It's now linear with respect to mu, which is again a locally finite measure. Okay, when alpha equals 1, this is the usual Newtonian potential up to some normalization problem. But what is important for us is to notice that in the special case when p is equal to 2, this linear potential coincides with the Wolf potential, because the exponent, remember, it is 1 over p minus 1, so it equals 1. And so we see that this Newtonian potential, for instance, when alpha is 1, is simply W2 mu. So it's a direct generalization of the Newtonian potential to nonlinear problems. Also, for instance, in terms of Fourier transforms, this Riesz potential I2 alpha is minus delta to the negative power minus alpha. And in fact, very important to us will be this fact that the nonlinear potential W sub P is actually, in a sense, equivalent to the inverse of the p-Laplacian. So in the same sense, basically, well, at least for positive measures mu, so as the Riesz potential is the negative power of the Laplacian. Okay, and to discuss this in more detail, to be more specific, let us talk about this equation where we have minus the p-Laplacian of u equals mu. Mu is, again, any locally finite measure on Rn. And let us assume, just to specify things, that the lim inf of this solution is 0 at infinity. And since mu is non-negative, it makes sense to consider the so-called p superharmonic solutions. When p equals 2, capital U is simply a superharmonic function. Okay, if I have time, I will talk about this in more detail. But what is important for us is this fundamental work by Kilpilainen and Mali. There is the famous paper in Acta Mathematica in 1994, where they proved that any solution to this problem actually is bounded from above and from below up to some constants, which depend only on p and n, by this Wolf potential. And so this justifies my claim that the Wolf potential is actually the minus p-Laplacian inverse applied to mu. Okay, so they proved these very important estimates for any solution U. Let me mention right away that uniqueness for this problem is in general is still open. Okay, it has been solved only for some classes of measures mu. For instance, for measures absolutely continuous with respect to capacity, something could be said about uniqueness. But in general, we don't know that. In any case, any solution to this problem satisfies such equations, such estimates. So inequalities 3. Okay, and also in my paper with Fook in 2008, we proved that a solution exists even only if this Wolf potential is not identically infinite, or which is the same, we have this condition 4. Okay, in particular, because of these estimates, a solution capital U is bounded on the entire space, even only if the Wolf potential is uniformly bounded, or which is equivalent in L infinity. But for instance, if you ask a slightly a related question, for instance, when do you have solutions which lie in the famous Bmo class? Functions of bounded mean oscillation, then the problem becomes much more difficult. So such estimates as 3 are not enough for solutions. You need the so-called gradient estimates for the gradient of this function, capital U. So I will talk about that. This is one of the goals of my today's talk. Okay, so let me continue then. And I need to introduce some weighted norm inequalities related to nonlinear potentials. Perhaps it is better to start with this inequality, the second one on this slide. You see this display here. So it's an inequality of Sobolev type, but it is non-standard because on the left, I have this LQ norm with respect to the measure sigma, which is less than or equal to some constant kappa times the L1 norm of the p-Laplacian of this test function phi, and we're assuming here raised to the power 1 over p minus 1, and those test functions should be again p superharmonic, and which means the minus Laplacian of phi is non-negative, and for simplicity, let us assume the lim inf is 0. Okay, so this is a basic inequality. As we will see, it is very closely related to sublinear or problems in the case where Q is between 0 and p minus 1. So this Wolf potential W, say P of mu, is finite at a single point. So it is not identically infinite, even only if this condition holds. And then, if it is true that this Wolf potential is finite at a single point, some point x naught, then it is actually finite almost everywhere and even quasi everywhere with respect to capacity. When p equals 1, this is a necessary and sufficient condition for finiteness of the Newtonian potential. So it says that the measures of balls should couldn't increase faster than the radius to the power n minus p. Okay, actually, it should be a weaker increase with r, the radius. So, as I said, we are going to study such weighted norm inequalities. Okay, and one can show that such weighted norm inequalities are equivalent because of those Kilpelainen and Mali estimates, two-sided estimates, I can replace this test function phi with this Wolf potential of the right-hand side. They're equivalent anyway. And then I can consider even measures new, not necessarily L1 functions. And so this inequality is equivalent to such a weighted norm inequality. And kappa here is the best constant or the least possible constant in such an inequality. Okay, it's a pretty complicated object, and I realize that, but this type of inequalities is fundamental to our problems, so you cannot avoid studying such estimates if you're interested in precise results. Okay. And so, for instance, this inequality is this one here, okay, in the integral form, or this one here in this differential form. So they are both necessary and sufficient, for instance, for the existence of a non-trivial super solution to this problem, and also for the existence of a solution if our solution is globally in LQ with respect to this measure sigma. But if you're interested in all solutions to this problem, then you need to localize it, right? Because generally speaking, you could be only locally in LQ with respect to this measure sigma. And by the way, this condition that U is locally in LQ is actually equivalent to saying that there exists a solution which is finite just d sigma almost everywhere, or even quasi everywhere with respect to capacity. So it's a natural class of generalized, say, super solutions or solutions, non-trivial solutions. Okay, so I need to introduce a localized version of those inequalities. So to do that, let us fix a ball in this Euclidean space, this ball B, and by kappa, which depends on B, let us denote the best constant in this inequality, inequality 5, where sigma here is simply restricted to this ball. So sigma sub B is my measure sigma restricted to this ball B. And on the right, I'm using this norm of the measure nu, but by this I mean simply the total variation of this measure. So it is nu of the entire space, the new measure of the entire space. Okay, but okay, so with this in mind, then by kappa of B, we denote the best constant in such an inequality, or this variational kappa of B could be used, which is the best constant in this inequality 6 now, okay, which is in this differential form, okay? They're equivalent, as we discussed earlier. Just to give you an idea of how to estimate such constant, let me state this lemma. It is proved in my recent paper, number 2, I think, on the publications list, but I need Lorentz spaces when S is equal to Q. This is equivalent to the usual LS space, Lebesgue space, okay? And let us assume that sigma is restricted to this measure B, okay? So here's this definition of the norm or quasi-norm, to be more precise, in this Lorentz space. And then we have pretty sharp estimates of this constant kappa of B in terms of Lebesgue norms. So this is the usual S space, but the exponent here is Q times P minus 1 divided by P minus 1 minus Q. This is the lower bound. The upper bound uses this Lorentz norm where the second exponent is Q. But in any case, this is very precise estimates, and you can obtain some estimates in terms of the usual LQ spaces from this easily. So with this in mind, I need to introduce this intrinsic nonlinear potential. And this is a crucial concept used in my work. It was introduced in my joint paper with Cow in 2017 in the Journal of Functional Analysis. So it looks similar to this Wolf potential, but in place of the measures of balls, we use these quantities, which are kappa of this ball. Okay, and so it's very similar to that Wolf potentials. It's of course a little more complicated, and recall that kappa of B here is this best constant in this inequality here, okay, for the Wolf potential. And so this seems to be pretty complicated, but you will see that estimates of solution in terms of such nonlinear potentials actually give very precise results, including bilateral pointwise estimates of solutions, and also uniqueness results, which follow from such precise estimates. But let us simplify all this setup and talk mostly about, first, about finite energy solutions. So what are finite energy solutions? So P is greater than 1. Let us assume P is strictly less than n because we are on the entire space. And W1P dot is the homogeneous Sobolev space or Dirichlet space, which is the closure of C infinity knot functions with respect to this Dirichlet norm here. And the dual space is denoted by W minus 1 P prime, the usual notation for the dual space of distributions of finite energy. Okay, then if we look at this equation, it is very well known that there exists a solution in this homogeneous Sobolev space if and only if mu has finite P energy, which is this expression here, which we can show is equivalent to the Wolf potential W sub P mu integrated with respect to d mu, okay, or it is equivalent to the Riesz potential of order 1 of mu raised to the power P prime dx. Okay, and this is equivalent to the Sobolev norm of this solution. Okay, all of this is a special case of this Wolff's inequality, which is due to Thomas Wolff, the famous harmonic analyst, and it appeared for the first time in this paper of Hedberg and Wolff in 1983 in Annals of the Institute of Fourier, and Hedberg gave some very important applications of this inequality. Okay, to theory of Sobolev spaces. But more generally, we have that even for fractional alphas, the norm of a measure mu in this dual Sobolev space is again equivalent to the Wolff potential W alpha P now of mu d mu, which is equivalent to the norm of the Riesz potential I alpha mu in LP prime raised to the power P prime. Okay, now let us talk about bounded solutions to this problem first. Okay, so here's one of the results which follows from my joint work with Kao Duck. It says that there exists a non-negative solution which is bounded, so U is in L infinity, uniformly bounded, if and only if the Wolff potential of mu is uniformly bounded and the Wolff potential of sigma is uniformly bounded. And moreover, there are global pointwise estimates. So those are good estimates, but please notice that the left-hand side doesn't match the right-hand side because of this, because I cannot, okay, because of this exponent on the left, you see P minus 1 over P minus 1 minus Q. So this result, when P equals 2 for the Laplacian on the left, and when mu is 0, so for homogeneous equations, is due to Brézis and Camille in that paper that I mentioned before. And also they established uniqueness of bounded solutions, and their proof is pretty complicated for uniqueness. I will mention a different proof which works for any solution, not necessarily bounded for this uniqueness property. Okay, so this is our result, but we have to improve our estimates, point-wise estimates, if we want bilateral estimates of solutions. Okay, here is a slight generalization to unbounded solutions. So here is this condition, which is common in studies of Sobolev spaces. Suppose that sigma of any compact set is bounded by some constant times the capacity of that set. So if this is true, then everything works as before, but this condition, which is shown in red, allows for unbounded solutions now. And the result is that in this situation, again, you have the same type of point-wise estimates if you add the Wolf potential to the power sigma on the right and the Wolf potential of sigma raised to this power. Again, the left-hand side and the right-hand side don't match, okay? But at least it works for unbounded solutions, some unbounded solutions. But if we know that the solution is bounded, then this capacity condition holds automatically. So this is a generalization of the Brzezinski mean result, for example. But to get bilateral estimates, we will need to use intrinsic potentials, okay, those nonlinear potentials. Okay, now let us discuss finite energy solutions. And here results are nice. By this, I mean they could be stated entirely in terms of Wolf potentials. So there exists a final energy solution to our problem if and only if we have two conditions, A and B, okay? So now this Wolf potential is raised to this exponent q plus 1 times p minus 1 over p minus 1 minus q, and integrate. You have to integrate with respect to the same measure sigma. And condition B simply says that the energy of this measure mu is finite. Okay, and these two conditions are necessary and sufficient. In fact, condition A could be characterized in terms of such weighted norm inequalities, which were studied by Mazia and Nitrusov. So they gave an alternative characterization of such inequalities, but they use some capacity functions. So condition A is actually simpler in a sense. Also notice that these conditions A and B are totally separate in terms of there is no interaction between sigma and mu in those conditions, but there is a lot of interaction between the first nonlinear term and the datum mu. Nevertheless, for existence, you can separate them. Also, such a finite energy solution is unique. Okay, but later on we will discuss uniqueness, if I have time for that, for any solution, not necessarily a solution of finite energy. Here is a slight generalization, but I think I don't have much time. So here, instead of solutions in the Sobolev space, some power of a solution is in that Sobolev space. But let me skip the details here. Next, let us talk about Bmo solutions. First, to this basic problem, where on the right you have a positive measure, mu. So we're talking about, solutions to this problem, which are in Bmo. Recall that the Bmo space is a special type of this Campanata space. So this is the space of functions locally in L1, where I have this condition here. And if, of course, if alpha is 0, then we have this Bmo space, okay? And if alpha is positive, but less than or equal to 1, then this is known to be equivalent for U to be alpha Hilbert continuous. This goes back to Campanata. Okay, so, and then we have this result, which is due to Kilpe-Lining and Zhong, which says that if alpha is strictly positive, then there exists an alpha Hölder continuous solution if and only if we have this restriction on the growth of mu on balls. So the constant c is, of course, independent of x and the radius of the ball. Okay. This is a local result, but you can also have a global result if you assume additionally that the Wolf potential is not infinite. So then it will be, together with condition 9, it is necessary and sufficient for the existence of a global alpha Hölder continuous solution. Okay, but the case when alpha equals 0 remained open, so this corresponds to Bmo results. When p equals 2 in the linear case, this was solved by David Adams in 1975. He showed that this u, which is the Newtonian or proportional to the Newtonian potential of mu, lies in Bmo if and only if we have this condition here. So alpha is 0 and p is 2. Okay, so this is for linear problems, but for nonlinear problems, we need new techniques, especially in this range when p is close to 1. This is the more difficult case. Here, using some Cacciopoli type estimates and also pointwise and integral gradient estimates, we prove the following theorem. So this is to appear in the Annals of the Institute of Fourier. So it says that there exists a Bmo solution to this problem minus the p-Laplacian of u equals mu, if and only if, again, we have this growth condition. So this is called sometimes a Frostman class of measures, mu. Okay, plus the condition which ensures that the Wolf potential is not identically infinite. And moreover, we actually show that in this case, when there is a solution in Bmo, it actually lies in any Morris space, but only when S is strictly less, only when this exponent S is strictly less than P, or in some weak form of the Morris space when S equals P. Okay, so this gives a characterization of the existence of Bmo solutions to this problem. But what if we have this term where the solution u is raised to the power q? And in the case where q is strictly less than p minus 1, we have a complete characterization of sigma and mu such that there is a positive solution in Bmo. It is given here, so the most important condition is condition A, so the measure mu cannot grow too fast, and also that constant kappa of the ball B cannot grow too fast. So these two are local conditions, and then there are conditions B, C, and D, which simply ensure that all the Wolf potential and nonlinear potentials are finite, and this is all naturally, and it is necessary and sufficient for the existence of a Bmo solution to this complicated problem. Now, if we impose this extra assumption that sigma of a compact set, the sigma measure of K is bounded by the capacity of this set, okay, then everything simplifies because we can only use, expressions like mu measure of a ball and sigma measure of a ball. So there is no need then to use those constant kappa. Okay, so it's much nicer. In any case, let me skip this generalization, which is a class of solutions. This is useful in applications in Sobolev spaces, but let me skip this. Okay, now what about general solutions, not necessarily bounded solutions or solutions which are in some fractional Sobolev spaces. And here is the most important result of my today's talk, which says that, or one of those results, which says that there exists a solution to our problem, equation 1, with lim inf of u equal to 0, for instance, if and only if we have these three conditions. Okay, so conditions 13 ensure that the Wolf potential of mu is not identically infinite, and the Wolf potential of sigma is not identically infinite. And condition 14 ensures that this intrinsic Wolf potential is not identically infinite. Then there exists a positive solution. Of course, all of this could be simplified under this restriction that sigma of a set is bounded by the capacity of that set, because in that case, this intrinsic Wolf potential is pointwise smaller than the Wolf potential. So you can drop condition 14, which is more complicated. Okay, so this is just the existence of general solutions. Uniqueness is more subtle, okay? Also, quite recently, and this should be the paper 2021, okay, anyway. So I recently, in that paper, I found two-sided estimates of all solutions. Okay, so on the entire space, whenever there exists a solution to our problem, it is bounded from above and from below by a constant which depends only on P and N and Q. And then you have this Wolf potential of mu plus Wolf potential of sigma raised to this power plus the intrinsic Wolf potential of sigma. So in my paper with Kao, this was proved in the special case where mu equals 0, but more importantly, the upper estimate was proved only for the minimal solution. Okay, and now I have those two estimates for all solutions. I mean, both the lower bound and the upper bound, which now match. Okay. So here, just let me remind you that this intrinsic Wolf potential is defined in terms of those constant kappa. Okay, so, and then sometimes people are interested in weak solutions. Okay, which means let us only focus on solutions which are in W1P log. Okay, and these are distributional solutions, so they're good solutions. And then when do you have a solution to this problem? The answer is that if you're interested in such solutions, then you have to add those two conditions, that the energy of the measure mu restricted to a ball is finite. This is the first condition. And also you have this condition that this generalized energy of sigma restricted to a ball is finite. So you have these two local conditions, plus, of course, you need those global conditions, which I mentioned earlier, conditions 13 and 14, because they needed for any solution. Okay, but with these two extra conditions, you ensure that your solution is a distributional solution locally in the class W1P. And those complicated conditions, for instance, condition 14 could be simply dropped if you have this extra assumption on sigma. Okay, now let me discuss uniqueness of solutions. And let me today focus on this case p equals 2. There are analogs for the p-Laplacian, but I don't have time to do that. And you have to be more careful with your definition of a solution. So let me focus on the case p equals 2. But in this case, I can allow for the fractional Laplacian minus delta to the power alpha. So let us look at this problem 18. So we're interested in solutions to this problem. Sigma and mu and u are all non-negative here. Okay, and the solutions are understood in the sense of this integral equation, where the right-hand side f is the Rees potential of mu when alpha is 1 it is the Newtonian potential of mu. So when alpha is 1, this is exactly the problem considered by Brézis and Camille for bounded solutions on the entire space. But in fact, we can prove uniqueness in a totally different way, even for general functions f, here not necessarily of this form. And here is my very recent result. It has been posted in the archive. So for this problem, there exists a solution f, some non-negative, say, Borel measurable function. So there exists a non-trivial solution if and only if you have, it exists if and only if each of the terms here is non-trivial. Also, we have two-sided estimates of solutions, as you see at the bottom of this slide. And moreover, such solutions are unique. So this covers all solutions, all generalized solutions to, for instance, this equation 19, not only bounded solutions. And the proof is based on my pointwise estimates. So it's a different proof because the proof of Brézis and Camille was based on relations to some parabolic porous medium equations, which are nonlinear and complicated. Okay, so let me just mention briefly concerning uniqueness that I actually prove it for general quasi-metric kernels. For instance, it covers complete non-compact Riemannian manifolds with non-negative Ricci curvature, or more generally when the heat kernel satisfies the Lie-Yao estimates. Okay, and also there is an analog for the p-Laplacian. And, but this is when q is less than p minus 1. So for q greater than or equal to p minus 1, solutions are known to be not unique. Okay, so those are remarks on the uniqueness property. So there is a new proof. Okay, so here's a nonlinear analog of Wolff's inequality. So remember that was an inequality for Wolff potentials. Now I have an analog for this intrinsic Wolff potentials, and this could be used to give necessary and sufficient conditions for the existence of a non-negative or positive solution to our problem. But now I require my solution to lie in the Sobolev class, for instance, globally. Okay, so then here you have two conditions only, and this is necessary and sufficient for the existence of a non-negative solution. And there is a restriction on the exponent r, but if r is strictly less than this cutoff point, then there are no solutions at all. There are no superharmonic, p-superharmonic functions. It's well known. Okay, so this characterizes the existence of solutions in LR, in Lebesgue classes. And there is a local version. Of course, the conditions are less restrictive. Okay, and then again, there is a complete analog of that result. But if R is strictly less than this cutoff point, then again, there are no even local solutions. So this answers the question of the existence of solutions in LR. And of course, everything simplifies under this additional assumption, which allows for non-bounded solutions. And here is just one simple solution. Here you have this fractional maximal function of mu. Okay, and let me just mention a few remarks. So we have those bilateral pointwise estimate of any solution. Okay, and even for bounded solutions, those two terms, you see this Wolff potential of sigma raised to the power p minus 1 over p minus 1 minus q. So this term appears in Brézis-Camille type estimates. But this second term, for instance, if mu is 0, there are only two terms. So it may have a totally different behavior at infinity or locally than this second term. And this second term allows to bridge that gap in the Brzezinski mean estimates, so that now we have bilateral estimates. And of course, if our solution is bounded, then we can show that the usual Wolf potential is larger than the intrinsic Wolf potential. So everything simplifies in that case. But in the LR case, you can use only the intrinsic potential. So be careful. Okay, so here you can drop the second condition, which involves the Wolf potential of mu. And BMO is kind of an intermediate case between L infinity and LR. And in that case, both nonlinear potentials are used in those results that I mentioned before. And finally, just very briefly, what about the supernatural growth case where Q is greater than P minus 1? There is no uniqueness question because generally for singular solutions, there are no unique solutions. But with regards to, for instance, the existence of BMO solutions, so here is necessary and sufficient conditions for the existence of a BMO solution to this superlinear problem if P is 2. The first condition, condition A, is so condition A here is actually necessary and sufficient for the existence of any solution. This was proved in my paper with Fook in 2008. But now for BMO solutions, you simply add condition B, and condition C, which restricts the growth of the mu measure of a ball and the sigma measure of a ball. But now there is an intersection between sigma and mu in condition C. And this is necessary and sufficient for the existence of a BMO solution in this case, supernatural growth case, okay, when Q is greater than P minus 1. Okay, so perhaps it is time to stop. So thank you very much for your attention.